Okay, normally I get a message saying it's recording, but it hasn't said that. But let's assume it is. Welcome to webinar 2, which is on calculus. And today we're going to be talking a little bit about national curriculum very briefly, and then we're going to be looking at calculus, which covers differentiation and integration. So national curriculum was introduced in 1989 in England. Maths was always a core subject, and basically the government was fed up of every single teacher being an island in their class and no one knowing what was going on, and everyone could teach whatever they fancied. Although obviously there were O-levels that everyone knew about, and they and GCSEs that then came in. So they had exams that were targets, so they knew roughly what was in it, but not a particular syllabus. So they provided the spec and then guidance about teaching ideas. And there's always debate about the content of the curriculum, and it comes and goes. In particular, as we've known over the last few years, there's been a lot about it's got too easy and the way the exams have become too easy, and that we need to increase the amount of higher level stuff in the curriculum, which has happened. But they've also introduced in particular the reasoning and problem solving that used to be there and kind of got quashed a bit as time went on. And it's a very broad curriculum, and so it's very difficult when it's so broad to achieve great depth, which is always the pressures that teachers have. And in fact, from next year, they are going to be revising the Maths A-level, and where they had split the Maths A-levels into lots of different modules, and you could select which modules you took, and you could go down taking statistics or mechanics or decision or a mixture. That comes to an end next year. They've decided that all students who take AS/A-level will do 3 exams at the end of the course. So they can take an AS. They will take the same exams, just shortened, if they finish at AS. Otherwise, they will continue for 2 years and then take the 3 exams at the end of the 2 years. And those exams will be maths and mechanics, maths and statistics, and maths and comprehension. There's no choice. Everyone will do some stats and some mechanics, and decision is now off the table. So that's a total turnaround from where it was. It has become much more, there was much more choice, and this is going kind of back to, well, the 80s, early 90s in terms of what was offered. So it's a bit of a shame. These are the aims of the national curriculum in mathematics. So become fluent in the fundamentals of maths, including increasingly complex problems, develop conceptual understanding, reason mathematically by following a line of inquiry, developing an argument, solve problems, applying maths to a variety of routine and non-routine problems. So really great aims that I don't think they're always realised. So just, thinking about what you've seen in schools and the content now versus what you learned, use of calculators versus mental methods. So in the A-level, for example, that's coming out next year, there's no non-calculator paper. They're allowed calculators for all of it. So that's a slight change. But regardless, with algebra, it doesn't make much difference if you don't really need a calculator. They've got rid of levels before you even started, so that's in there because a lot of schools still talk about levels and it's still ingrained anyway. But really, technically, they're sort of not around anymore. So sort of the attainment targets. And how does the curriculum impact on your department, on your planning, on the freedom to choose what and how you teach? And do you think there's room for exploration of teaching, or is it just teaching for the test? So, any comments you want to make about any of those things? Do you think what you're doing is about the same, what you're teaching is about the same as what you learned?
Oh, sorry, I had myself muted there. I don't know, I'm thinking that kids are becoming too reliant on electronic methods to do maths now, and they forget that it's been done for thousands of years without calculators and stuff. And as for teaching to the test, yeah, we've got to teach them, but I think allowing them the opportunity to investigate and explore themselves gives them a greater knowledge and understanding of the topic. I mean, you teach someone by rote, yeah, they'll know it, but they won't understand it.
Yeah.
It's that between knowledge and understanding.
Well, good. Hang on to that and keep remembering that throughout your career. Try to make sure you're always doing that, because I know it's so easy to get back into, or not get back into, but just to fall back on telling them what they need to know, rather than just, because there are these pressures, and sort of, getting them through. And I don't know if your school gives them little tests and stuff every so often, but obviously you want them to get through those. But I think, especially when you've got years 8 and 9, those are the times when it's a good opportunity to let them fail things and give them freedom to explore, because there's no harm in it. It's better that they then start learning things for themselves, because you're right, not just the use of calculators, they're doing things mentally. There's also very much this just reliance on us to just tell them things versus being bothered to use their own brains. So we definitely need to keep challenging that. So anyway, that was just a little bit of discussion about maths curriculum before we get on to, oh good, Mark's joining us. Yay. Let's just wait a second then while he joins us. Hello, Mark.
Hello, how are you?
I'm good. Are you all right?
Yeah, not so bad. Sorry about that. I had registered for the webinar, but I couldn't find it on my email links.
Oh,
and then
sorry.
so I was trying to find it back going through Student Central. I was like, oh, I can't find it. Where is it? And then found it eventually, but I don't know what happened there because I did originally register it. And then when you first put it on, that's when I registered.
Oh, okay.
So I don't know. I don't know what happened there. Obviously, it didn't work properly. But there you go. I'm here.
Good. Okay. Well, so far, all I talked about is we just briefly talked about the national curriculum, which was just basically saying about, how you used to be free to teach whatever you liked. Obviously not in my time, this was 1989, before then. But just a general sort of discussion about what you think about the impact of the curriculum. And we were just saying, keep letting the kids explore as much as possible and learn reasoning and problem solving and all that stuff. But what we're doing today in terms of maths is calculus, which gets a bit confusing when you talk about differentiation, obviously, because in a teaching perspective, we talk about differentiation. But today we're going to talk about differentiation and integration, mathematical calculus, and really useful parts of AS A-level. Used to be at the top of GCSE O-level. I remember doing one of my GCSE coursework when it's differentiation. But it's my favourite. It's my favourite. We've got a lot to fit in because previously this was in 2 webinars, or actually I think I did it a face-to-face, and I've kind of squeezed it together. So I've reduced it as well. It's not too bad, but it's going to be quite intensive. So calculus, the study of differentiation and integration, was developed in the 17th century. Now, it was done by 2 people at the same time, Newton and Leibniz, who argued their whole lives over it. Newton was a fairly unpleasant guy by all accounts, and he was determined that he had come up with this first, but actually evidence suggests that Leibniz, well, they did happen to come up with the same thing at the same time in a different way. So calculus is really useful for solving problems involving motion, and that was the way I think that Newton was coming at it, whereas I think Leibniz was coming at it from a more pure perspective. But you know, for studying the planets and flights of rocket, and when Newton was all involved in the study of motion, that was how he got involved in it. Calculus can be used basically to study any situation. It's all about rates of increases or decreases, so rates of change. So in a distance time graph, the speed is given by the gradient of the graph, because gradient is change in y, the change in the distance over change in time. Now, so this is the rate of change. So speed is a rate of change. It's the rate at which the distance is changing over time. So what calculus, what differentiation basically does, is looks at the gradients of graphs. But it's all very well when it's a line. More of the question is what happens when it starts to be curved. How do we find out information about that? And that's where calculus comes into it. And I think Newton was doing a lot of this, but Leibniz is the one, his notation is what we actually use. So for AS, candidates are expected to understand about the gradient of the curve, and we will, and why, how they developed differentiation. I will talk to you briefly about it, and it used to be included when I was at A-level, but nowadays what we call differentiation from first principles is not actually included. However, I haven't checked the new syllabus for next year. So understand how to differentiate basically and apply it to problems. So that's what we're going to look at now. So this is what we call first principles. This is how they came up with it. So if we think about the graph of y equals x squared, we've got a parabola. What we're going to do, in order to find the gradient of this curve, we're going to zoom in at particular points. So here's our curve. If we zoom in where x equals 2, as we get closer and closer to it, we can see that what looks like a curve starts to look more like a straight line. And thus, we can then basically say, okay, let's say it's roughly a straight line, it's a chord. We can find 2 points on it and find the gradient. So yeah, it looks very straight. So by drawing tangents all the way around, we can find the gradient at each of those points. So the gradient is the difference in the y values over the difference in the x values. And at each point, we're going to measure the rate of change at each point, so how y changes with x. So, here we go. So this is the key thing about differentiation, which seems a bit arbitrary, but without it we wouldn't be able to calculate the gradient. So what we say is the gradient of a point on a curve, so at this point 2, 4, is the same as the gradient of the tangent at that point. And that's the whole point about tangents. And when we're talking to kids about drawing tangents on their graphs, and they are often wildly inaccurate in terms of the steepness, they don't seem to appreciate that the gradient of the tangent where it meets a particular point should be the same as the gradient at that point. So it should be in exactly the same direction. So having drawn this tangent here, we can then pick any 2 points on our tangent and work out the gradient. There we go. So it's gone up 12 there and along 4. Along 3. Yeah. So my gradient of this tangent is going to be 12 divided by 3, which is 4. The gradient at that point is 4. Now I'm going to quickly then click through all the way to show you as it moves. So at -3, the gradient is -6. At -2, the gradient is -4. minus 2. So when it's flat, the gradient 0. At the point 1, it's gradient 2, point 2 is gradient 4, and so on. So what we notice is for each point in the curve, these are our gradients. What can you spot about that? Is there a relationship between the gradient and the points in the curve? Either of you? What can you see is happening between the x-coordinates? Yeah, Mark.
Yeah, it's basically that it's the gradient is effectively double the x-coordinate, isn't it?
It is.
In this particular instance.
Yes. Have you done differentiation before?
I've heard of it.
Okay. So I know that's good. So that is basically the pattern you've spotted. Yes. So for the x-squared graph, the gradient is twice the x-coordinate.
So would that then mean that it's going to be 3 times it on the cube graph, or am I just like going too far?
No, you're almost there. Let me show you.
6.
So in fact, what we could write. So if I show you the x-squared one. So for x-squared, the rule for differentiating is that it's 2x, so 2 times the x value. We write this as dy by dx. That is the notation that Leibniz came up for describing what we call the derivative. Well, there's so many words for it. The derivative, the differential, basically what we get when we differentiate. And it's basically the gradient because it means it's the difference in the y values over the difference in the x values. So that's where that comes from. So we say dy by dx equals 2x. That is the formula for getting the gradient at any point on the graph of y equals x squared. So that's quite cool now because you could say, okay, well, how do I know what the gradient is on the curve at the point when x is 3? Well, we know it'll be 6. Okay, so yeah, so that is the gradient function. Now, if we look at x cubed, I'll do the same thing again where it's going along. So we've got x cubed, so at minus 3, it is 27. So this is a bit weird. What it's doing below is plotting the x-coordinate and the gradient. We'll see why in a minute. So at the point minus 2, the gradient's 12. At minus 1, it's 3. At 0, it's 0. At 1, it is 3 again. At 2, it's 12 again. And at 3, it's 27. So the way that these gradients go, actually, the gradients of these are exactly the same as the gradients of those. But you were almost there saying, is it cubed? It's not, oh, sorry, it's 3 times. It's not quite that. I don't know if you can spot it. It's quite tricky. Any ideas?
Is it perchance? Right, it's multiplied by whatever the x-coordinate is, times the cube.
Times 3.
No,
yeah.
I did have that right. Yeah.
So, which is in fact.
So obviously, yeah. So when you got x is minus 1, it's going to be 3 because it's 3 times that. Then when x is minus 2, it's going to be 6 times that. X is minus 3, it's going to be. That's right, because that would have been more, wouldn't it?
Oh, well, so, I mean, this is a difficult sequence to work out, you know, and it is, in fact, if you square the x value and then times it by 3, you'll get it. So minus 2 squared is 4, times 3 is 12. Minus 3 squared is 9, times 3 is 27. So there you go. It is, in fact, 3x squared. And I guess part of the hint is that the gradient function that's been drawn there, as you can see, is a parabola. So you'd know it would be some sort of x squared function. So that's the relationship for an x cubed graph. Now, if we just quickly think about the line y equals x, What is the gradient of y equals x?
1.
Yeah. And the line y equals 1?
0.
Yeah. So this is quite useful because what it does is sets up a whole table that we can do. So when we've got the graph of y equals 1, the gradient is 0, so it's flat. When we've got the line y equals x, the derivative is 1. X squared is 2x. X cubed is 3x squared. Any guesses what x to the 4 might be?
4x cubed.
It is. It is. And so x to the 5 is 5x to the 4. So this is the pattern for differentiation. What we say is in fact I've got this in the next page. So here's the pattern. So the pattern is we bring down the power and take one off the power. So we write it like this in general formula. So for any function which is written as ax to the n, so if we had a number in front, the number in front just stays there. We bring down the power, so we multiply by the power, and we take one off the power. And that's differentiation. So that gives us, for any graph that we have given that's a polynomial of this form, we can simply bring down the power and take one off the power, and we've got the gradient function. So we are then able to find the gradient at any point on that curve. So have a go at doing that now with these four. So bring down the power and then take one off the power. You've always got to do it in that order, otherwise it'll get muddled. Is that alright? Can you have a go at doing that? And if there's a number in front, then when you bring down the power, you just multiply it by that number to bring them together. Mark, if you mute yourself, it's like a buzzing noise.
Okay.
Right, Mark, do you want to start us off? What to get?
Right, I think I've got this right. I might have gone slightly right towards the end. Is it? I've got 8x to the 7th.
Yep. That's right.
Then this was confused me a little bit. I simply got x to the 0, which is 1, isn't it?
Exactly. So because that's written really as x to the 1 when we've just got x, when we bring down the power, it's like there's a 1 in front, and we take, 1 off the power, you end up with 1x to the 0, which is basically just 1. Exactly. So that's why that still obeys the rule. Hugh, what did you get for C?
6x squared.
Yeah. And what about D?
20x to the negative 5.
Yes, good. So you bring down the -4. -4 times -5 is 20. Take that off the power. Good. Did you get that, Mark?
Oh, nuts.
Have you?
I went the wrong way on the minus.
-3.
I put it to -3. Yeah.
Yeah. And
as soon as he said -12, I was like, what are you talking about? And I spotted it. Yeah.
Yeah. Every kid does it. All of us do it from time to time. Hugh, if you just mute yourself, please.
Sorry.
So yes, that is why I put that one in there, because it was so easy to make that mistake. I mean, the students struggle with negative numbers anyway, and then they're thinking, okay, wait, which way am I going? I'm taking one away, so -5, and it is really tricky, and especially if you're doing it quickly, it's easy to go the wrong way. So always take care with negative numbers. Okay, they've then written it like that, but it's not necessary. You can leave it as negative numbers. Now, this is why I sort of said, oh, you're going to need your indices, because more often than not, for that sort of extra bit of testing your indices, they'll give it to you like this. So you always have to write it in terms of the correct powers and then differentiate. Okay, so that, I know it's in there, but that's a 3 in part D over the cube root of x. So for each of these, so that one, just apply differentiation. And these ones, you need to write them first as powers before you can do everything with them. Okay, so have a go at doing those, then put your hand up when you've done those. And you don't feel you have to convert them back. You can just leave them as powers. Right, Hugh, do you want to start us off then? What did you get for the first one?
This is very tentative, as I'm a bit concerned I've made some mistakes.
Mm-hmm.
But I've got it as x to the negative 2/3.
Yeah, that's right. Again, you know, students, as you can imagine, really struggle because not only is it fractions, but it's fractions going into negatives. So yeah, no, that's correct. And do you want to do B for us as well?
I believe it is 3/2x to the negative 1/2.
Yes. Oh,
Thank God.
no, that's right. Yeah, so you bring down the power, so that's 3/2, and take 1 off the power, and you get the minus 1/2. Yeah, that is right. Mark, have you done the C? I know it's mean to leave you the two really hard ones.
Okay, well, I think I've got C, and I was trying to work a few things. So, going on the theory that the square root of x is x to the minus, or is x to the half.
Yes.
I went the idea that it might be slightly wrong here, that the cube, the square root of x cubed will be x to 3/2.
That is right.
Okay, which then left me with 3x over the half.
3x to the half. Yeah.
3x to the half, yeah.
Yeah, that's right.
Okay. The last one confused me a bit because I'm not very good at rationalising thirds. I might have gone slightly wrong here. I started off trying to multiply it by cube root of x over cube of x.
You don't need to do that.
Okay, then I've gone well off. Yeah.
Just write this as a power. So x to the root of 3 is x to the third. And when we have sort of 1 over x to a power, that's what it means to be negative. So that is actually just x to the minus a third, this bit. And then we've got a 3 as well. So you don't need to, let me do it like this. So if I had 1 over x, that's just x to the minus 1. Yeah? Is that right?
Yeah, that makes sense.
So if I've got 1 over root x, that's just 1 over x to the whole. So yeah, that's x to the minus a half. And here, because it's a cube root, it's just because it's to a third, so it's to a minus a third. So anything that's over, so when it's on the bottom of a fraction, it just means that you can make the power negative. That's the relationship between them. Yeah. So that makes it much easier than...
yeah, and then because you've got the 3 over that, you can just bring the 3 down for 3x minus third.
Yeah.
Which then has made you, yeah. It made you would have been minus 4x over 4 thirds.
Yeah.
Yeah, because minus 1.
Yeah, so it just gives you a minus 1 there, x minus third times 3. Take 1 off, you get minus 4 over 3. So yeah, I mean that's a, you know, like the toughest one they'd be given. You know, it's harsh when it's got a lot of indices working it, but obviously that's kind of the expected, you know, build up of knowledge over the AS. So they then converted it back, but I don't think you need to bother. So if you just mute yourself again, thank you. So differentiation from first principles is no longer examined. It used to be, just when I started teaching. It's only been in the last, I don't know, 5-6 years that it's not been examined. There used to be little questions about it. But basically where that formula came from is that if you draw a graph, So this is in fact the x squared graph. You draw the x squared graph and you think of a point x, then your function will be f of x. So if this was the starting point of x was 2, and you chose something very, very, very close to it, so the point 2.0001, then your gradient would be your change in y, so your 2.0001 squared minus 4, over your change in x, which would just be 0.0001, which would give you a gradient of 4.0001. As you got closer and closer to 2, so if you got smaller and smaller numbers that were closer to 2, you get an even better approximation to this. And that's basically what's happening here. So if we take a value x and we choose, this is like really, really zoomed in, we've chosen a value of h that is really close to it. So this is some number very, very close to x. Then our value for our function will be f of x plus h. Then our gradient is going to be the difference in the y's, so the f of x plus h minus f of x, so that's the difference in our y values, over the difference in our x values. Well, if the difference in the x values is x plus h minus x, the difference there is just h. So that's our gradient at sort of between these bits. And what this bit is saying, this limit as h tends to 0, is if you imagine making h so tiny, tinier and tinier and tinier and tinier, so this would come down, 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 until effectively it was just a dot. It was the same point. So as h basically goes to 0, so this means the limit as h tends to 0 of this gradient of this chord effectively becomes the gradient at that point, which is what the derivative is. So this is the first principles thing. And where we were writing dy by dx, in function notation, we can write that just as f dash of x. Okay, so that's just like a little apostrophe. It's just difficult to show. I should just put it. Just does it in weird fancy writing for some reason. So, as this says, it's the rate of change of the graph or the gradient of the tangent of the graph. Now, this means that for each graph we've got, like x squared, x cubed, we can derive that formula from first principles. And I'm just going to show you this because it's no longer examined, but it's nice. And I think even though it's not examined, I still show students every time. So because we're talking about the change in the y's over the change in x, and the limit as that gets smaller and smaller, we can put this all in terms of x squared. So if you think about the graph that we had, it's an x squared graph. If this is my value of x, then my equivalent y value is going to be x squared because that's what we do to x. So what's going to be my value, if my x is x plus h, what will my y value be? So if this is the graph y equals x squared, what do we do to x each time? Yeah, Mark?
Would it be x plus h brackets squared?
It would be, exactly. So for any graph, we can basically put this, what seems, this very generic definition, we can find what these values are. I'm now going to find what's going to go on as well. So there you go. So our change in y is going to be our x plus h squared minus x squared, and the difference in x is still h. Now if we multiply all of this out, we get x squared plus 2xh plus h squared minus x squared over h. So we can cancel the x squared minus the x squareds disappear, and we're left with just 2xh plus h squared over h. So we can divide through by h. There we go, they're taking that out. Cancel the h's. We're left with simply the limit as h goes to 0 of 2x plus h. But what this bit means is, if h is going to basically be 0, as that happens, and this bit gets smaller and smaller and smaller, at the point on the curve you're going to be left with 2x. So that's basically differentiation from first principles. That's how Newton or Leibniz got that first formula. Well, that's how they proved the first formula, because I'm sure that they also just spotted that it happened to be close to 2x and thought, why is that? And then came up with the reasoning. Now, do you guys want to have a go at doing x cubed yourselves, or would you rather move on to stuff that is the elements? It's up to you. This is going to involve you doing some multiplying out of cubics. So it can take quite a lot of time.
Yeah, I'm still quite sketchy on the about cubics, and even that bit you just did fried my brain a little bit. So
yeah, I think no, this is deep stuff. So I will leave it on here so that obviously you can see it. But I won't get you to do it, I think. So, and this is the sort of thing that actually, I guess, if I had a top set or really, a class that you think would definitely be interested, like especially with further mathematicians who are going to be wanting to go on to do maths, possibly at university, you'd do this sort of thing. But otherwise, I have done it before with lower ability classes. And yeah, the problem is that obviously it takes absolutely ages to multiply out a cubic, so they get caught up in that. But here we can see if we multiply it out, the x cubes cancel again, and again, we can then cancel out the h's. And what we find is that because the h is going to be 0, the h squared will disappear, that bit will disappear, and we're left with 3x squared being the formula for the graph of x cubed. So that's what we discovered before. So this is the more typical sort of question that you'll get. Find the gradient of the tangent to the curve f of x equals x squared and x equals 5. So the process we go through, we want the gradient, so we need to find the gradient function. So we differentiate the x squared to get f dash of x, or you can write dy by dx. It's only because it's not written. If it was written y equals x squared, then I would generally write dy by dx equals 2x. Because it's written in function notation, f of x, I just write it, I keep writing it in function notation, so I write f dash of x. So that is the gradient function for this curve. I want to know what is the gradient at x equals 5. So I simply substitute in when x equals 5, and f dash of x is 10. So that's kind of the sort of basic level of question that the students get. So finding the gradient of x squared. More of an application would be this sort of question. So smoke from a factory chimney travels at route t kilometres in t hours. Calculate the speed of the smoke after 4 hours. So the speed is just the rate of change. So they're expected to realise that to calculate the speed, that is the gradient of the distance when it's put against time. So they need to differentiate this function. So they generally need to call it something, either f of x or y. So here, in fact, they're going to call it d of t, so the distance travelled. So d of t is root t. So d dash of t is what we want. Now let's write t in an indices as a power, as t to the half. We differentiate that. We're going to get half t to the minus half. We want to know how far it's travelled after 4 hours. That's when t is 4. That actually, I suppose, is quite helpful to go back to in this occasion, because it's easier to think of it as root 4. But they do have calculators in this paper, so if they really couldn't get their brain engaged, they could just type in 4 to the minus a half and hopefully realise what they've got. So when we put in t as 4, we've got root 4, that's 2, multiplied by 2, so that's 4, and then 1 over that is a quarter. So it's gone a quarter of a kilometre in 4 hours. No, sorry, the speed of the smoke after 4 hours is a quarter kilometres per hour. So yes, the speed. And that's just at that particular point, because it's always changing because of the nature of this curve. And all you can say is you can only say the rate of change at a particular point. This gives you the rate of change as a function over all the points, but it's only a quarter kilometre per hour at that point. So, if you've got a number of bits to the function, it makes no difference. You just do it bit by bit. So 8p to the half minus p, just differentiate term by term. So we differentiate the first term, so half 8 is 4, take 1 off, half, so 4p to the minus half, and then we look at the minus p, and the minus p is like minus p to the 1, so bring down the 1, take 1 off, so it's p to 0. So that's simply what we get, 4p to the minus half minus 1. Okay, so when you've got multiple terms, you just treat each term as a term and just do each bit. If you've got this sort of thing, you can't differentiate while they're in brackets. It needs to look like a polynomial with different terms. So you need to sort all of this out first. So multiply out the brackets, divide by x squared. So if we multiply out those brackets, we get x squared minus 2x minus 15 all over x squared. So this is where the indices work really comes in. X squared over x squared is 1. Minus 2x over x squared means we have 1 less x on top, so 2x to the minus 1. And here, you're dividing by x squared is the same as times by x to the minus 2. So you could, if it helps you, you could have a line in between. It depends whether you think it's easier to think about dividing by it, or where you multiply by the fact that this is 1 over x squared is the same as x to the minus 2. So this is like multiplying all of that by x to the minus 2. But it's just a case of your indices laws. So this is x to the 1. So when you divide, x to the 1 divided by x to the 2 is 1 minus 2 to get you minus 1. This one, it's as if there's an x to the 0 there, and 0 minus 2 is minus 2. Now, the problem is that a lot of students get into is they're like, oh, great, okay, I've finished. I'll put in x equals 5. All we've done is sort out the y. We haven't yet differentiated. And it's so easy to forget that. So, oops, I didn't know. So when we differentiate that term by term, the 1 disappears because x to the 0, when you bring it down times by 0, that disappears. When that does disappear, be wary of the minus, which belongs to this 2. Minus 1 times minus 2 gives us 2. Take 1 off, we've got minus 2. And minus 2 times minus 15 is 30. Take 1 off is minus 3. So there's a lot of bits and bobs involved using indices. And then remembering that you haven't yet differentiated, so you need to differentiate. And then you need to remember to put in the x. So the gradient of the tangent to the curve at x equals 5 of this graph is 8/26. Which I can't really think of it as a decimal, but 0.8. It's nearly a third, isn't it? So, here is one that's got kind of everything. It's a bit mean for me to like nudge you in it. Mark, is your hand up to ask a question, or was it left over from before?
Yeah, sorry, that's left over from before.
Oh, that's all right. Obviously, if you have a question, just say it. So, here we've got, actually, I'm just going to click on this today. I'm not going to get used to it. Here we've got kind of everything involved. So, in an exam, this is more like an exam question, where they've got to translate to obviously what the word's saying, realise what they have to do. Then they've got to sort out this using all their indices knowledge. Then they've got to, do. Then finally they get to do the differentiation and plug this stuff in. So I want you to have a go at doing this now. Okay, Hugh. So what do you get first for the function when you sort it out?
I think I might have made a mistake here,
Okay.
but I'm getting the function of 4 take 3d to the half over 2d to the negative a half.
Ah.
I think I made a mistake. I can't see where.
Okay. Let me click through. I got this because in between, so the root d that's on the bottom, 1 over root d is like 1 over d to the half.
Ah, yeah, that's where I made the mistake.
Yeah, so it's d to the minus a half.
Yeah.
Yeah, so when you times those along, d times d to the minus a half is like d to the 1 minus a half, which just gives us a half. And 3 over 2 minus a half just gives us a 1.
Yeah, I see where I made the mistake now.
So hopefully that's a bit nicer than the one that you had. How did you get on, Mark?
I think I was along the right lines, but what I ended up doing, I got myself confused with what I was doing. I figured out the root d is d to the half.
Yeah, that's fine.
And then I completely forgot what I was doing, and for some reason had a brain fart and simply just threw it up to I have 4d minus 2d to the 2/3 and d to the half. I just completely forgot to divide the other half, and that screwed me over.
Yeah, and that is so common as well. When faced with something like this, the kids, because I've said to them, just differentiate term by term. They do each bit, forgetting that that actually is only true if I've got nice linear looking terms with no divisors or anything. So yes, all of differentiation and integration comes back to a really sound knowledge of indices. So being able to manipulate these quickly can then get you onto the rest of the question. I think that's where a lot of our students fall down because they're spending obviously quite a long time having to sort this out. But they spend so long doing that they don't think they're finished. But basically when we differentiate this, well, what do you get? Having a look at it now, what do you get if you differentiate out? Yeah, Mark?
Okay, I've got that, and I differentiate that down as 2d to the negative half minus 2.
Yeah, good. So when you put the 4 in fact this time, again, it can be a quite useful time to write that back. So d to the minus a half is again 1 over root d again. So it can be useful to do that, because then when you sub in the 4, it's fairly straightforward. So you end up with 2 over 2 minus 2, which is actually just minus 1. So that must be about here. It looks like it's about minus 1, isn't it, there? That might be about 4 meters in from the start. But as you can imagine, seeing this sort of thing can really put off a lot of the kids because there's so much involved in it. Whereas if so they're absolutely fine when you say, here are the questions, differentiate this, differentiate this, differentiate this. Fine. They apply this formula. It gets a bit more complicated when they've got indices, but then when you put it into a question, then you've got to be showing them lots like this, because that's much more likely to happen. Now, what they also like to do, as well as just getting them to differentiate, is to use differentiation. Now, the stationary points on a curve are the points where the gradient is 0. So here we go, this is a graph, an x cubed graph, x cubed minus 2x squared times 9x. The stationary points are here and here, where the gradient's 0. And it's also called turning points. So we've got one max and one min. Finding those can be really useful. So before, when we were factorising this, we were finding the 3 points where it crosses, but we could only roughly draw it. We didn't know where the turning points were. Now we can use differentiation to find those exactly, so you can draw a more precise graph. So yes, they are known as local maximum min, but no one really calls them out, just the maximum. So, in order to be able to do this, we can look at what's happening on either side of the stationary point. So if we look at this maximum, as it says on the left, here the gradient's positive. It then becomes 0 at the top, and then on the other side it becomes negative. So that means if we have got a maximum, this is the sort of shape that we've got for a maximum. This is what's happening with the gradient. It goes positive, 0, negative. For a minimum, it's the opposite, isn't it? So it's negative, and then 0, and then positive. So if we want to know whether we've got a maximum or a minimum, we look at what's happening either side of them. So this sort of question is very typical. Stationary points are very useful because it can be useful to know in real life situations the maximum of something or the minimum of something. But if we think about what's happening with the graph, the gradient is 0. So if we take our graph and differentiate it, so our x squared minus 4x plus 1 in this case differentiates to get 2x minus 4. At the stationary point, we know that the gradient will be 0. Now actually I also know, because of the fact that it's a positive x squared graph, I actually know it's going to be a positive parabola. So that's quite useful for the students. You know, as a mental check, you think if it's an x squared graph, it should be like this. So I'm expecting to get a minimum. But now we have to go through and basically demonstrate that. So we've differentiated it. We know that at the stationary point, the gradient will be 0, so we can make 2x minus 4 equal to 0. And solve to find x. So x is 2. To get, it asks for coordinates, so what's the x and the y? That's another thing that's often forgotten. So we put the x back into here, we're going to get 2 squared minus 4x plus 1, and y is minus 2. So the stationary point is at the point 2 minus 3. We don't know just from getting the coordinates whether it's a max or a min. Now we know, because we have a knowledge of x squared graphs, that it's probably a min, it should be a min. But to test that, we can look at the gradient either side of x equals 2 and see what's happening. So if we substitute in x equals 1 into the gradient function, we'll get 2 minus 4 is minus 2. So we can see that the gradient to the left of our coordinate is negative. And if we do the same with x equals 3, we can see that to the right it's positive. That's exactly what we're expecting, isn't it? Left, negative, 0 at the point x equals 2, and on the right of 2 it's positive, and therefore it's a minimum. You don't have to go a whole point, but it's it's easier. If it was a really tiny graph with lots of turning points, you might have to go just 0.5 either side. So you did 1.5 and 2.5. But in this occasion, because there's only one turning point, we know that everything's going to be negative to the left and everything's going to be positive to the right. Does that make sense? Is any of that you want to ask me about? Okay, because that's sort of the key reason why calculus is useful, because we can think about where it's got maximum and minimum points, make it equal to 0, and find those points. Another way, so we can either just look at the gradient either side, or we can think of the fact that here we've got the original curve, which is an x cubed graph. They've drawn the gradient function, which is an x squared graph. And if we were to think about the gradient of the gradient function, so at the minimum here, the minimum of the x cubed graph, if we look at here on the graph, the overall gradient here is positive. So when we have a minimum, what's happening is we're going from negative to positive. So we're basically, the gradient is going in a positive direction, as you can see from this graph of the gradient function. Whereas with a maximum, it's going from positive to negative. And so as it changes, it's negative, basically. So what that means is the gradient of the gradient function. So if we were to differentiate the gradient function itself, we would get another gradient function, which would tell us about the nature of the stationary points. And when we do this again, we call it d2y by dx squared. That's how we say it and write it. The kids find it a bit tricky initially to get used to about where they put the 2's. I don't know why we do it like this, but this is just the notation that Leibniz came up with. So if you differentiate the gradient function, again, you get what's called the second derivative. So this is called the first derivative. It's got so many words for it. First derivative. The second derivative is d2y by dx squared. So if we differentiate that one again, there's our original curve. We've differentiated it, which has given us the first derivative, the gradient function. We differentiate the gradient function, we get the second derivative, which is written d2y by dx squared. And we just do the same thing again. So we bring down the 2, take them off. So 6x plus 6 is the second derivative. Now, because that's only telling me about the nature of the gradient function, but remember not to use it to tell you anything about the original curve. What it's telling us about is the nature of the stationary points and whether they're a maximum or a minimum. So, find the stationary points in the first place, we find when the gradient function is 0. So we're going to make this quadratic equal to 0. And this is just solving quadratics now. So we factorise, and we discover that it's got 2 stationary points, which is not surprising because it's a cubic, the original graph. So the 2 stationary points are x minus 3 and x is 1. We can pop those into y. And our points are minus 3, 37 and 1, 5. So we could look at the gradient either side of that by looking at minus 4 and minus 2 and see whether it goes negative or positive in which way, and the same with that one. Or we'll just differentiate again to get the second derivative and substitute each of those values in. So when x equals minus 3, the second derivative, d2y by dx squared, is minus 12. So it's negative. So what I said before was when we have a maximum, we go from positive to negative, positive to negative. So that's shown on our gradient function as a negative, and therefore our second derivative, showing us the gradient of this gradient function, will be negative. So that negative tells me that this must be a maximum at the point when x equals minus 3. And equally, if I think about a minimum, just going from negative to positive, and shown by the gradient function there, the gradient of the gradient function is positive. So d2y by dx squared for x equals 1 should give me a positive, and therefore it's a minimum. I think that students don't always remember or understand why it's negative or positive. Ultimately, it doesn't matter. They don't need to know why. They just need to be able to recognise, oh, look, I've differentiated again, I got a negative, so it's a maximum. And they kind of think to themselves, oh, a lot of them think, oh, it's just the opposite to what I think. Like a max, you'd think it would be a big number, but in fact it's a negative, so must be that. Min's positive. So whichever way they like to remember it. So a lot of them find it easier to think about what is happening either side of the gradient. And that's absolutely fine. However, some questions ask them to do it particularly by finding the second derivative. So they need to know both ways. They need to know both ways as well because there's a third type of stationary point. So minimums and maximums are very straightforward because you can see what's happening with the gradient either side. And the second derivative will tell you that. But if you do the second derivative, sometimes it can give you the answer 0. And then you don't know anything. And that can actually happen with any of them. It just happens to be that it was the gradient function was changing at that point as well. So when they're close together, you might get a 0. Then you have to look at what's happening on the other side. And one of the possibilities is that you get what's called a point of inflection, where it's come down. So in this case, it is actually negative. It's stopped briefly and become stationary, and then it's continued to be negative. And so at that point, the second derivative is 0. So in that case, you've got to look at what's happening with the gradient either side, because if you get negative 0, negative, then it is in fact what we call a point of inflection. But happens less regularly than minimums and maximums. But it isn't possible. So that's quite a lot going on there. And there's lots of terminology, and lots of it's very similar. So at the point that the gradient is bigger than 0, so it's positive, we say the graph is increasing, whereas when it's negative, it's decreasing. And then at the stationary point, it isn't doing either. It's not increasing or decreasing because it's 0. So this is just saying you can determine whether a stationary point, so we say the nature of the stationary point, that's determining whether it's maximum, minimum, or inflection by looking at the standard gradient either side, or by looking at the second derivative. And this is just summarising what we've done. If it's less than 0, it's maximum. If it's bigger than 0, it's the minimum. If it equals 0, it could be any of them. You've got to check the gradient either side. So I haven't accepted anything to do, but on the self-studies I have, there's a differentiation self-study and an integration self-study, which I've put up on Student Central, where you can practice all of this. because it's very involved. There's lots to do. So going through step by step, and I get the kids to definitely write out their steps, where I sort of say to them, okay, first of all, you've got to sort it out if it involves weird indices. Then you've got to differentiate. You've solved to find the stationary points. Then you differentiate again, put in the stationary points, decide whether they're max and min. So I generally go down the route of using the second derivative because it's quicker and often gives you a result right away. Then, if that hasn't helped me, I check the gradient either side. Does that make sense? Okay, I would take that as a yes. Obviously, what you need to do is have some more practice of it. This is something that the students will be doing all year, and forgetting even in the exams. I just want to show you, before we have a quick break, one of the ways that we use this. So finding stationary points can be quite a bit of fun. One of the things that I do, and what I would do if I was with you, is to get you to take a 10 by 10 piece of square paper and cut a square out of each corner. And I always do with this with the kids. And then you say to them, okay, I want you all to make a box. So they cut out a square from each corner. It's got to be a square. They fold it up to make a box. And you'll get some of them doing these really tiny, skinny boxes, and some of them doing really tall ones. And you basically want them to tell you, so they calculate their lengths based on what they've cut out, and then they calculate the volume of the box. And you get them to work out which value of X will maximise the box. Some of them are right idiots. They cut a 2.5 centimetre square, a 5 centimetre square out of it, and then they scored their box. So they obviously realise the constraints fairly quickly. But what they end up doing is then, and this is the extra step to differentiation, is they have to come up with an expression first before they can even differentiate it. So they haven't even been given the expression, they've just been given an example, like this. So here we've been given a farmer's fence. It's 100 metres long, and he's going to enclose, he wants to make a rectangle for his sheep, let's say. And he's got a hedge along one side, so he just needs to put it around 3 sides. So we want to know, well, how should he do it? What length should this bit be and this bit be to find the maximum area so he can get as many sheep in there as possible? Do you think that you could have a go at this without me saying anything more?
No.
But this is the sort of thing, when I've taught them differentiation, obviously they've had maybe 2 weeks of doing all this practice that you've not had. And I would just give them this, or actually I tend to give them the one with the squares, with a cut square, and get them to see if they can do it. They really struggle. It can take a whole lesson. So yeah, that's why I was, unless you had a massive flash of inspiration, it's quite hard going on a webinar, unfortunately. But let me show you. So coming up with an expression, if this is 100 metres all the way around, I've got to define one of the lengths myself. So if I say that this length is X, what's this length going to be?
That's going to be X again, isn't it?
Yeah. So then what is that
So
going to
you
be?
could almost go with that. You could call that Y, and therefore say that 100 minus 2X equals Y. Start from there.
So, well, I don't really need the Y itself. I can just say that's 100 minus 2X. What I'm trying to find, and this is what you've always got to think about, is area. So how do I calculate the area of a rectangle?
Length times width, so in this case it would be x times 100 minus 2x.
Exactly. And there we have our expression. So that's all they have to do, but breaking down those steps of reasoning is something that they really struggle with. And these are the sort of things that I expect us to be able to do at GCSE, you know, just coming up with these sorts of expressions. But they do struggle with that. So ultimately, we've got a equals, if I multiply it out so we can do something with it, we've got a equals 100x minus 2x squared. So now I've got a function that I can differentiate. So what do I get when I differentiate? What will dA by dx be? Q? What do I get when I differentiate 100x minus 2x squared?
Just 100 take 4x.
It is, yeah. Now, based on what I was saying before, I want the maximum area. So what do I need to do next? How do I find the maximum?
Is this where you do the second differentiation?
No.
Is that it, or am I going the wrong way?
What do I need to do first? How do I find, when I was finding the stationary points, what's happening at the stationary point with the gradient function?
Okay, you got for a maximum you've got negative one side, positive the other. Sorry, other way around. For a maximum you've got positive one side, negative the other, as in the gradients.
In order to find where that maximum point is, what is happening?
Your gradient has
Yeah, your gradient has to be 0, exactly. So that's the first step. Find what the point is when your gradient is 0. So 100 minus 4x equals 0.
so
what's
25.
X is 25. Yeah. So if x is 25, this is going to be 15. So your max area is going to be 25 times 50.
Yeah, 1250.
Now, for good measure, we should really check that is a maximum. So that's when we then differentiate again. So if I do d2a by dx squared, what do I get when I differentiate this again? So what do I get if I differentiate 100 minus 4x?
You're going to get 100 again, aren't you?
No, the 100 disappears.
100 minus 4.
The 100 itself
Oh, of
disappears.
course, yeah, because it's the minus what if it goes to the 0, doesn't it?
Yeah.
So you get basically, that's just 1, so you end up with 1 minus 4.
Ah, well, no,
3.
the 100, if I do it over here, the 100 is like having 100x to the naught. So when I bring the power down, I get naught times 100, and basically that's all naught. So it's like having naught minus 4.
Yeah.
So it's just minus 4.
Yeah.
But that, again, no, that is exactly what the kids do as well. It's an easy thing to fall into because you're like, oh, I'll leave that bit and then do this bit. And then they end up with 96 or something.
Yeah, because I was thinking 100 to the 1 rather than 100x to the 0.
Yeah, that's it. So minus 4, negative, so yes. Luckily, it's a max. And it's because in this case we didn't have a choice, there was only one. But in the one before with the volume over force, because it's volume, that's cubed, there's 2, there's a max and a min. So that is differentiation. Have I put anything else? Oh, okay, I'll put another one. You guys can have a go at doing that one another time. Because it's, but I mean, this one at least, hopefully the kids would think, okay, well, that actually has an actual use to it. I don't anticipate that many farmers will actually use calculus to sort of working it out, but they could. And obviously, if you've got an enormous farm and you need to really, segregate each bit, then it'd be useful to have someone working with that, and not have to use trial and error. So that is differentiation, and there's another one here I've done about max and min, where I'm doing it like that. But I think we've got lots to get through, I'm afraid, today. So all of it's on the slides, and you can go through it in your own time, before you do the self-study. But let's take a break now and come back at 5 to 11, and then we'll do integration. Okay?
So at 5 to 2, what time do you have now? Because I've got 2 different times in front of me.
Oh, I've got that it's 1:45 at the moment, so 10 minutes. Take a 10-minute break.
Okay, yeah, got that. Thank you.
Okay? Great.
Yeah.
Okay, see you in 10 minutes. Right, hello.
Hello.
Right, is
Greetings.
right. Sorry, I was just going to hit it. Freezing. Right. Integration is the opposite of differentiation, and so we are now basically going to do the opposite of what we've been doing, which is why when it's all in one in the webinar, it's very confusing, and obviously would not be taught all at once. Generally would take, you can spend a good 5 weeks just doing differentiation and integration sometimes. So hopefully they don't get too confused. But actually the thing is that when they then get to the exam, they do very easily get confused. They're just, struck by, oh, I need to do something with powers, which way is it? You get a bit confused. But if you think about differentiating, if we had been told that our gradient function was 2x, you'd think, okay, so it's probably the graph of x squared. But because the numbers disappear when you differentiate them, because they're like x to 0 and it disappears, actually, you could have had all sorts of translations of x squared. So x squared plus 3, x squared minus 4. So when we go back the other way, if our derivative is 2x, we have to say that our original graph was x squared plus c, some constant c. And that's the general solution. We might then be told a point on the graph, at which point we can then substitute that in and find out what c is. Don't forget the constant. The students do, and one person I saw on Twitter made, every time their students forgot a plus c, they had to decorate this and put it on the wall. So they ended up with all these plus c's all over the wall every time they do it. But anyway, whatever gets them to remember, this is the notation that we use. This is, it's a very, what it technically is an elongated S, because when we derive, how can I say derive? When we come up with integration from first principles, it's we get it from looking at areas under graph and summing up lots of little areas. And so this S stands for summation. But basically it is the integral sign. And it's joined, it is basically coupled with this dx in this case, which means integrate with respect to x. Because you could have functions with different letters in them, which would be way too complicated at this point, but this is saying we want to integrate the function here, and we're integrating with respect to x. Those wrap around the function that you integrate. The students always forget this, and I get more annoyed probably by that than I do with the plus c, because if they forget the plus c, they get the whole answer wrong and then they know it, but they don't seem to care about the fact that it's just good grammar to put the dx in, otherwise you haven't completed the sentence, basically. So if we integrate 2x with respect to x, we get back to our function x squared plus c. And so because the previous rule was bring down the power, take one off the power, in order to reverse that, we add 1 to the power and then divide by the new power. Okay, so if we have this one, 2x, let's see there's a 1 there, so we add 1 to the power to get x squared, we divide by the new power, and so we end up with 2 divided by 2 is 1, and that's how we get the x squared by itself. Written in general notation, the integral of x to the n with respect to x is add 1 to the power xn plus 1 and divide by the new power. So they put it all at the front, but basically divide by that, plus the constant. If you've got x to the minus 1, you can't integrate that at this point. this, can't apply this formula to it, because you end up dividing by 0, which is undefined. But there's another way of doing that involving logarithms. And this is again saying if you are integrating something that's got lots of terms, you just integrate it term by term. So, as I've said, students get muddled with differentiation, or they divide by the power instead of adding 1 to the power first. And these are called indefinite integrals because we are, well, we'll do definite integrals later where we get numbers and they're creating areas. Indefinite integrals generally take us from a gradient function back to the original graph, whereas definite integrals take us from a graph to the area of the graph. We'll look at that in a minute. So, to integrate this, oh, it's done it all at once. I add 1 to the power, so x to the 4 over 4, plus 6x, there's a 1 there, so it is for the 2 over 2, plus c, and then I sort that out. So I cancel down 10 over 4, and I cancel down that 2 over 3. So that is what you get. That was the original graph, or it's a family of curves, if you don't know what this is yet. That you get that gives that gradient function. Now, you guys integrate this. So add 1 to the power, divide by the power. And then put your hand up when you're done. Right, so Hugh, what did you get?
I got 4/3 x cubed, take 3/2 of x squared plus 2x plus c.
Good. So easy to lose that 2. So lots of the students, again, just because they're looking through it, and they're like, oh, it's a number, differentiation, they disappear, and that ends up going, but actually that's 2x to the 0, so when you add 1 to the power, there's 2x to the 1 over 1. So that's good. 4x cubed over 3 minus 3x squared over 2 plus 2x plus c. Is that all right, Mark, as well for you?
I missed it because I thought the +2 was a constant.
Yes. Well, so exactly. So that's why.
So I just left it as +2. Yeah.
Right. Yeah. So that is also it's as if there's a 2x to 0 there. So that becomes 2x. Good. Have a go at a longer one then. Actually, that's a bit easier, isn't it? Okay, so you should have got all of them cancelling out. So you actually get x to the 5 minus x to the 4 plus x cubed plus x squared plus x to the 2. Is there any issues with that? Okay. So if you're given the gradient function, when you're asked to find the general solution to this differential equation, that just means integrate it, and remember the plus c. But then when it says find the equation of the curve with this gradient function, which costs 3.110, we then substitute that in. So we integrate it to get our original family of curves. We want to know, that's the general solution. We want the particular solution. So we substitute in that x is 1, y is 10, and rearrange it to get c equals 4. So our equation of the curve is y equals x cubed plus 2x squared plus 3x plus 4. So, I mean, I can't think of a situation, in fact, where if you take a gradient and have to come up with a curve. Although, if you wanted to create, you were building a ski slope and you wanted it to be particular gradients, gradients of, certain gradients, and then you're like, well, how can I get the slope of it? Then, you might want to do this one. Right. Again, this is just saying simply integrate this function. You've got to sort out your powers first, but if you just integrate that, so first of all, write it as as a power, as a fraction, and then integrate it. Mark, what did you get?
Okay, I got 4 over minus 3 x to the minus 3.
Oh, you've gone the wrong way again with the negative numbers. Because, yeah, when you add 1.
Of course, I'm adding this to minus, so it should be x to the minus 1.
Yeah.
So 4 over 1 times x to the minus 1.
Which is why I put this in there, to catch you out.
Yeah. Yeah.
Yeah. So it's just...
So effectively then, so you actually end up with negative 4x to the minus 1, don't you?
Yeah, yeah, which is nicer than the 4/3.
Yeah.
So yeah, it is just a case of thinking, which way am I going? And I have days when I look at it, I just can't make sense of it, negative numbers and which way they go. So how the students could always be just so it's equally. Just one of those things that when your brain isn't tired, it's really hard work to think about. Was that all right with you? Yeah.
Yeah, because the way I wrote it down was negative 4x to the power of negative 1 plus c. But that's just the same as how you write it all the way around.
Yeah.
Would they get people to leave it in that form?
No.
Okay.
Some people just have preferences.
Yeah, that's just what I wanted to
yeah.
It looks right.
It is right. Yeah. And yes, I would definitely have left it as minus 4 x to minus 1 plus. Yeah. That's what I would have left it as. In an exam, there is absolutely no reason to faff about putting it back into a different form unless they specifically asked you, which is fairly unlikely. Well, sometimes they will have done it as a show that you can get there. But otherwise, I mean, there's no need. It's just personal preference a lot of the time. Some people don't like to have negative powers, but I prefer to leave everything just as it is, because then it's most useful and, doesn't cause extra work. So I'm not with you, so we won't do a calculus next. Right, so as we've seen, we can take the gradient function, integrate it, and we get the original curve. However, integration is most useful for areas. So when we integrate the gradient function, we get back to the original function. If we integrate the original function, we get an area function. So you can kind of see how we have this sort of sliding scale of area function, original function, gradient of the gradient function, and we can sort of go back and forth between those. Now, the reason for it is all because of something called the fundamental theorem of calculus, which is about, this is why we use a summation sign, because it's about the sum of all these tiny little bits over time adds up to, what it says is the net change of the quantity. I got that from Wikipedia because I was trying to find a useful way of writing this that was fairly straightforward. It's not something that you or the students particularly need to know. I did it at university and did know it fairly well and have a depth of understanding of it that I just don't possess anymore. There is a good video showing it on Teach Pure Maths, what's it called? I'll put them in one of the resources I showed you. And it's this guy from the late 90s, I think it's from the University of Leeds, just talking it through. There was one point where I used to show the students this. It would be like a Friday afternoon when we wanted to just sit and watch a video, basically. I don't think it actually made any difference to their lives, so I stopped doing it. But basically, all you need to know is that if you integrate a function, you get the area function. Oh look, I did put it there. I used to show this video, integration and summation. So there it is, Maths Centre. Now on Maths Centre, this guy did masses of videos for teaching A-level, and they were brilliant. At the time when no one, video, teaching via video things were quite new. It was so like, oh look, I'm going to show my class this video, and then I don't have to stand at the board doing it. They can watch a video of someone else standing at the board doing it. But they're very straightforward, which is lovely. So here is a function, 4x cubed plus 4. We want to find the area under the curve between 2 points. So here we go. Here's our function. Between x equals minus 1 and x equals 2, we want to know what that area is. Now this could be useful in just an example if we have used this to model something, I don't know. So let's say we've used it to model a slope and we need to dig out that slope and find out how much earth we'll have if we've done that. We can find the area, although that would be volume, wouldn't it? Let's imagine that we live in a two-dimensional world, and then that will all be okay. But if we want to know the area between these 2 points, we can integrate, and we have the 2 points written below and above the summation sign. I actually put them a little to the right. So when we integrate, instead of writing plus c, we put a square brackets around the function instead. And we write our 2 points on the outside. And what that means is then substitute this one in, and by substituting in the 2, that will give me all the area to the left of 2. So it will give me all this area and all the rest beyond it. And then, if I substitute in the minus 1, that will give me all the area to the left of minus 1. So I do the normal distribution with you briefly. It's the same sort of premise of that. I mean, that's where the normal comes from integration rather than the other way around. But it's basically that what you're doing when you're substituting the numbers, finding all the area to the left of it. So in order to find between 2 points, we do all the area to the left of it, take away all the area to the left of the other point. So we substitute in the 2, So 2 to the 4 plus 4 times 2 minus 1 to the 4 plus 4 times 1 minus 1. We'll pull that out. And basically, this area here is 27 units squared. So the integration bit is exactly the same. You've just got to then have the numbers and substitute them in the correct order, taking one away from the other, taking the correct one away from the other. The students find this confusing. They add it. They've forgotten fundamentally what is happening with the graph, that they're doing everything to the left, taking off everything else to the left. So they just get confused. So let's not worry about it with area at the moment, but just evaluate this definite integral. I mean, it is technically finding the area between 4 and 9, but it's just giving it as a simple question without anything on it. So integrate this, put it in square brackets, substitute in the 9 and the 4 and take them away from each other. Have a go at doing that now. Oh, you're going to struggle if you don't have a calculator. Well, you might not actually. You can get there quickly. Mark, how have you got on?
Okay, so assuming I've got my integration right in the first place, I've got finished off with 84.4.
Yay, me too.
Rock on. Have
So
that.
there you go. Yeah, so it becomes 5 over 2 over 5 over 2, which you can switch around when you divide by fraction, comes 2 bits. You sub in the 9, and yeah, I did the same as this. I square rooted first and then did it to the 5. And why did it 2? Oh, because it's square rooted first, isn't it? But anyway, whatever you do, you get 84.4. Good.
Yeah, I must admit I didn't do it that way. To be fair, your notation was far different to mine. I ended up with when I differentiated out, I ended up with x to the power of 5 over 2 divided by 5 over 2. So I just switched it out to decimal. So x to the power of 2.5 divided by 2.5, and I did it that way.
Right. Okay. Yeah. And I think a lot of people prefer that because they don't like fractions. I tend to stick with the fractions, although when I got to here, I then actually made it 84.4 as well. I didn't make it 2.4. Whatever suits is fine. Yeah, good. Is that all right, Hugh?
Yeah. So in all honesty, the only reason why I changed it to the decimals is because that's easy to type into a calculator.
Well, yeah, I guess it is, yeah. Hugh, is that all right?
Yeah, I got it. It's just the calculator decided to stop working, so I've had to use the one on Google. I had to finger it all in with brackets and everything.
Yeah, and so what I did, because I was like, oh, I need a calculator, I thought, oh, if I square it down first, then I get this, the 3 to 5 and 2 to 5, which I know those ones.
Yeah.
And then I used a calculator actually because I have got one. But you could do this in your head.
Yeah, I didn't spot that 9 and 4 both square numbers.
Yeah.
I spotted that.
It can become quite complicated anyway. And advise, if you teach this ever, advise that the students write out each bit and don't try and skip steps. Because, I mean, when I mark this, generally they get 1 mark for getting the thing correct. They get 1 mark for each sub they put in and for taking them away in the right order. So I need to see that they have subbed it in correctly. They're generally a 6-mark question integration because it's only the bits to it. Now, if you have areas below the x-axis, they are in fact negative. And so it's often useful to draw a sketch. So for example, find the area between the curve and the x-axis for x squared plus 3x between -1 and x equals 2. If you simply calculate this, in fact, let me do it. Okay. If I just integrate this, I'm going to get x to the cube, x cubed over 3 plus 3x squared over 2. And I do it between -1 and 2. So I'm going to get 8 over 3 plus 6 minus a third plus 3 over 2. Not sure what that is. But 8 over 3 plus 3 is 9 over 3, so that's 3 plus 6 is 9 minus 1.5. So I'm going to get 7.5. So if I just calculated the area without drawing a curve and just did it, I would get the answer of 7.5. Now, having looked at the curve, if I integrate between 0 and 2, for that first, right, let me delete my bit. Remember that it'll be 7.5. Okay. So if I integrate this bit, I get 8 2/3. And if I do the other bit, b, between -1 and 0, I get that it's negative and it's 1 1/6, which is why when I did the whole thing, I ended up doing 8 2/3 and minus that, and so together that gave me my 7.5. But when we think about the actual area, we're talking about a positive amount. So although it's given you a negative answer, there is still an area of 1 1/6. So we've got 1 1/6 there and 8 2/3 there. So we actually want to add those two things together. Whereas doing it all by once takes them away. So it should actually be 9 5/6 square units is that total area. So it's just something to be really wary of. And hopefully they would have either given you a curve so if you didn't know it, or led them through the question, getting them to sketch the curve and then find the area. So they generally do that. If they just ask the area and they haven't drawn it, the expectation is that hopefully it should be correct. But they like to do these ones where they've led you through and got you to realise that there should be 2 bits you have to do separately, and then you ignore that negative and add them together. So your turn now. Find this, just the definite integral, and then do a sketch and find the area. Okay. I will help you by doing the sketch. Oh no. Oh, hang on, I did it wrong again. Do you agree? And then you can always check whether you agree with the scores that I've put all over the screen. So how far through are you guys?
I've just started again for the 4th time.
Oh no.
I've finished and got down to 21 and a third.
Good. Okay.
But I'm still trying to work out how to actually sketch the graph.
Yes.
I've literally got down to the point where I'm literally gone down to x equals -1, -2, x is -3, -2, -1, 0, whatever, and then trying to just basically work out what y would equal each occasion, just so I can figure out what the graph is, so I know what the hell it is I'm supposed to be doing.
So, if you look up at the screen, you see it's a quadratic. So I multiplied it out, so I got 4x minus x squared. I don't know why I did that actually, because actually I then want to factorise it, so I can find where it crosses the graph. So it crosses when x equals 0, or when 4 minus x equals 0, so when x is 4. So I know those are the 2 points that it's going to cross, and because it's an x squared graph, it's a parabola. And because it's a minus x squared, it's going to be a negative parabola. So this all comes back to quadratics knowledge. And often this would be wrapped up in a whole question, because it would force the students to go back to what they know about quadratics, so they don't have to sketch that, and then identify what bits it is. Because you're absolutely right, if you can't do that, then, so the first time I'd drawn it wrong, because I'd multiplied it out incorrectly and was doing it over a different graph. So I was finding the area between different bits in a different graph. So yes, you need to be able to identify first of all the bits that you need, and that's tricky, isn't it? Were you all right with integrating this one at the top? Did you get 0?
I never even got around to the integrating. I was too busy trying to do the sketch.
Oh right, okay. No, that's why I did it earlier. Because I thought that is the tricky bit, because that's not what we've done today.
So I did have a go to start off with, and I think I ended up with I never got as far as getting it to 0, in all honesty.
Yeah.
Because I think that's partly what it was. I was getting something I didn't really understand. I was too busy trying to think, okay, I've got to subtract something and add something, and yeah, I just completely screwed myself over.
And this is it. Once they get to A level, every single question is made up of everything that's come before, so it's very involved. And obviously, yeah, if you fall at the first hurdle, then it's a bit of difficulty. Often they do show that questions, so that they'll have said, it will have asked them to sketch the curve or hinted to them in some way what it looked like. But yeah, so going back over quadratics work and indices work will be very valuable for you, I think. Because then once you get to the actual integration, it's just time consuming really, and you end up getting quite a lot of the same when it's like this. Now, there are lots of slides after this, so I've got half an hour, so I will go on a little further. I put a sort of stop there because I wasn't sure how much longer, how long it would take. And we have obviously rushed through some massive topics, so I don't expect you to be getting this right away. But if you have got two curves, oh there you go, sorry. The area between two curves you can also find like this. If you think about what we're doing when we integrate, as well as finding it to the left of the point, we're finding the area below the curve. So if you integrate between these 2 points here, 0 and 3, that will give you the area under that curve all the way to the axis. And if you integrate this one, then the same thing, it will again give you the area underneath it. So in order to find the area in between them, you can do it separately and do the area under that one, and then take off the area under that one to give you the area in between. Alternatively, we can actually do the taking away. Sorry, that's just one of the intersections that we cannot obviously see. They've done it using sort of case so we see it. So yes, you can do that. It's the area of all of the x plus 1 graph minus the area of all of that one, and do the integration. Or you can actually combine these straight away into one big integral. It doesn't matter which way you do it, but you could do it so that you've then got what, minus x squared x minus plus 3x. Yeah, so that would be it, minus x squared plus 3x. But it's not strictly necessary. Now, what I wanted to show you, as well as doing integration and getting areas, we do something called numerical integration, which isn't really integration. It's an approximation for integration. So when we think about the area under a graph, and if you were to just give this to the students, so I've started in many different directions for integration. Sometimes I've just gone, like I have today, and done the reverse of differentiation. Other times I've just given them a load of curves while starting with straight lines and asked them to find the areas underneath the graph and work that way. It's difficult to decide which one works better, really. But this one, I suppose, is more investigative. So what they'll tend to do is they'll draw triangles or rectangles underneath to approximate it, and then they'll give me a rough area. And obviously the smaller that they draw their rectangles, the closer they can get to it. Here we go, like this. So you can give them some graph paper, they can split it all up, calculate those areas, and get a better and better approximation, an estimation for them. So the key thing is that the greater the number of strips you have, the better is the estimate. And by summing all of these together, that's what gives us the approximation to integration. And this is particularly useful if we've got something that we don't know how to integrate. Because that's 2 to the power of x, we don't know how to integrate that at this precise moment. There won't be something I'll be going into either. So we need to estimate this using our own method. Now the thing about the rectangles is they go over the tops of these too greatly, so you have quite a big error, basically. So better approximation is a trapezium. So here we go. We've split it up into 4 trapezia, all of equal width, and that's going nearly almost the same as the curve. Now, the area of a trapezium, I don't know, can you remember the formula for an area of a trapezium?
Is it something, no. Height by top to bottom, isn't it, divided by 2?
Yeah, yeah. So, there we go, there's a trapezium. Yeah, so it's the parallel line, their lengths added together. It's called the average of the parallel sides, basically, because you add them together and divide by 2. And then multiplied by the distance between them, which is the height. But anyway, it's half a plus b times h. It used to be given in GCSE papers and is no longer given. So it is something that they're expected to know from GCSE. So if we know one, if we know that formula, we can now find the area of the estimated bit that we've made under the graph. To find the values of A and B, well, we've made these trapezia by drawing between the points on the curve at each of the x values. So when x is -1, we can work out what y is, and that will be y0. When x is 0, and so on. So, as it says, the height of each trapezium can be found by substituting the x into the function. So our function will be made up of the first trapezium, our area will be made up of the first trapezium, which is going to be half a plus b, so our a is y0 and y1, multiplied by h. Our second trapezium is going to be half y1 plus y2, multiplied by h. Our third one will be y2 plus y3, multiplied by h. And our fourth one will be half y3 plus y4, multiplied by h. Now, because they have a lot of common factors, we could take out the half and the h and put that at the front. We can also see that in terms of adding all these heights together, all of these ones in between where the trapezium meet are repeated. So we've got y1 and y1, y2 and y2, y3 and y3. So we've got 2 lots of each of those and only one of the end ones. So we can rewrite this so that we've taken the half and the h out. There we've got all of them added together. And we can group those so that we've got the y0, then we've got 2 of all the y1s, the y2s, the y3s, and just one y4. And you can use that formula to calculate each of those heights. The area under that graph of 2 to the x. You can equally just do each trapezium, but this is basically the trapezium rule. So as part of AS, they're also supposed to know the trapezium rule, which is an approximation to integration using trapezium. So this is what it is. The integral of the curve between A and B is going to be the half h, so this is what we've extracted from it. And then we've got 1 y0, that's our initial height of the first trapezium, plus 2 lots of however many there are in between, plus your final height. Now, they then do this. This is the formula. This is given in the AS-A2 formula booklet. And it says the height is b minus a, which is basically your two ends x coordinates, divided by the number of strips. So sometimes they might get you to calculate it with 8 strips, sometimes they might get you to calculate it with 4 strips, and sometimes they might get you to do both and compare the two and say why one is better than the other. The key thing is all the trapezium must have the same width, so that this h is the same all the way through. Often it's going to be either a half or 1, something very typical. So here we go. This is the graph of 1 plus x squared, all rooted. They want to know the area between 0.5 and 2.5. So we're going to split it up into 4 trapezium, which are each 0.5. And I can tell that because if I do 2.5, so h is b minus a over n, so that'd be 2.5 minus 0.5 over 4, which is 0.5. So what I do is I set up a little table of each of my x values, so 0.51, 1.52, 2.5, and I sub each of those into here to get my y values, and they've been done for 3 decimal places. Then I can sub all of that into here. And I've got some students who prefer to just do that, and some who like to add another bit to the graph so that they remember that they've got one of those, and they do that calculation. They've got 2 of each of these. So they do that working out here rather than when they get into it. So it's because they don't like this notation with the subscripts and this one's y naught, this one's y on. They get a bit confused about the language. They understand that they only need 1 length of the first one, 1 length of the last one, and everything else is double. So they prefer to do it this way. So they work all that out there. They know that that bit then is what's in their brackets, and they just need to multiply that. And we used to call this smiley face. And then we used to say that half times the height, so that's basically the width really, the distance of each trapezium, which in this case is 0.5, times smiley face, gives you the approximation of that area. So in this case, that's going to give you 3.679. So that's just because quite a lot of students don't like to write it all out in here and can be prone to quite a lot of error just in writing it down. So I think I prefer to show them sort of as a table, and then they do the other bit, and then they just need to multiply that. So we would never have been able to integrate this, but we can find an approximate area using trapezium rule. And these are nice. That's a nice question. I mean, because that is something that you could give the students. They could just use trapezia and GCSE knowledge to approximate stuff and come up with it. They could definitely develop that themselves, so that they feel attached to the trapezium rule. I would definitely advise against just telling them this, as I've had to do with you guys, because it is definitely something they can discover. So, if you guys have a go now, we've got time, yeah, we've got time. use the trapezium rule with 4 strips to estimate this area here. So between, in fact, sorry, no, it's between 2 and 4. This is the integral that we're doing. So between 2 and 4 is here. So they want 4 strips. So your trapezium, oh, it's so straight. Yeah, there's the first one. Here's the second one. Here's the third one. Whoops. There's the fourth one. So always beware. What are these numbers? Where are we going between? How many strips? And then you can complete the table by subbing each of these in. So the first one, 2 minus 1 is 1. Square root is still 1. So our first y value is 1. So calculate the rest of these. And then this is r times h times smiley face, which is 1 naught. That's 2 lots stepping in between. Okay. So put your hand up when you've done that. Hugh, what did you get? Hugh, what did you get?
Oh, sorry, I've just been talking there and on mute. I
I
worked it
did
down
wonder.
to, yeah, I've worked it to a 2.79, 3061,334.
Yeah. 3
Yeah.
significant figures. What were you going to say?
No, I was just saying yay. I thought I'd unmuted myself, sorry.
No, that's all right. I had my first webinar last week with cohort 4, and there were long periods of time when I was thinking, I think one of them just muted themselves, and that was the problem, that they just were talking and had no idea whether we couldn't hear them. So yes, the sort of putting it all in, multiplying each of those by 2, it's definitely a calculated job. These ones always are. And keep the answers as accurate as possible for as long as possible. Mark, how far have you got through it?
No, I come up with exactly the same answer as Hugh, and this is the first thing I've understood since 84.2.
And I think so. I think maybe this is definitely the place to start with integration. Yeah. You start with areas. You give the kids loads of graphs, and you just get them to spend lots of time doing the trapezium, and you can introduce the trapezium rule, and then you can say, well, for some of these graphs, actually, you can actually calculate them and come up with a pattern. If you get them, I have got a sheet that I think I've uploaded. Hopefully, let me see. This one. So this has got generic ones like this. So that's y equals 2x, y equals ax, 2x plus ax plus b. So once they've then worked these out, the areas, they might be able to find, hopefully, a relationship between that and so on. And you can keep this going so that they then spot integration and the formula for it. And then they might spot, oh, that's the opposite to differentiation. So I've uploaded that. Good. Now, does the trapezium rule give an over or under estimate of the area under this curve? Let me show you the curve again. What do you think?
Curve though, doesn't it?
So, but is the trapezium, are the trapeziums giving you an underestimate? Or
well, in this example, it's going to give you an underestimate.
Exactly. Why is that?
Here's the curve is positive, like
Yeah.
we
refer like that to mirrors, concave and convex. So, okay. Oh, that's not very good. But if I try and exacerbate it like this, so when it is concave, the trapezium will come in underneath it, and so it will be an underestimate. When it's a convex graph, the trapezium will come in above it. I should have done them much more like that. There you go. So it comes in above as an overestimate. So that's often coupled with the question. So they get them to do the trapezium rule, and then they ask them these 2 questions. How you can make your approximation more accurate? You always just say more trapezium, more strips. So I've uploaded all of those onto Student Central. I'm going to go back to sorry. this slide. So I had to say the additional slides available, but not sufficient time, but there was sufficient time. Obviously, you didn't have much time to do very much on this. But, sorry, Hugh, can you just mute yourself, please? Okay. But there are 2 self-study tasks up on Student Central, differentiation and integration, and they're just doing practice of them. Oops, I could show you those. So here's the differentiation one. It's just finding the gradients at a point, finding where the gradient is 4. That's like finding where it's 0, but it's just making it 4. Finding stationary points, so maximum stationary points. There's a farmer building the wall. So that's differentiation 1. And I've just managed to shrink everything away. There's an integration 1 as well. So those are both up on Student Central. Now technically, according to when you're supposed to be doing things, the differentiation 1 is like December and the integration 1 is January. But, you know, do them, I would do them fairly shortly whenever you can to reinforce this and sort of get to grips with this. And then I don't speak to you again until January. I think, let's just get rid of this. So, yeah, you've got these 2 self-study tasks to do. So I don't speak to you again until the 20th of January. So we've got very few webinars. In fact, we've just got 4 webinars. So I see 1 in January, 1 in February, and that is it. And then I see you for the intensive study week, and that's it. That is it. Very sort of front-ended this year. So at the next webinar, we're going to be doing sequencing series, binomial proof, again, quite a lot of stuff. And then we've got exponentials to do and so on. So do the 2 self-studies. I have done all the self-study tasks by hand, and I'm just debating whether I just scan those in and upload them, or whether I type them up. So we'll see. We'll see how I get on with starting to type it up. If it's being really laborious, then I'll just scan them in and upload them so that you can check your answers. Or email me at any time. You can email them to me, and then I can tell you what you've got right and wrong. But either way, I will soon put up, well, I won't put up the answers to the ones you haven't had yet, but I'll put up the algebra one, and then I will, no, I guess I will just put them all up as I do them. So yes, you've got these self-studies to do to practice differentiation and integration, but your assignment is due basically on that first day that I see you in February. And I was talking to Hugh about it beforehand, Mark. Are you clear about the assignment, given the guidance we're given this week?
Kind of, yeah. It's basically, I've got to get my head around it because I've been thinking about far too many other things since then.
Yeah.
Since we last talked about it. It's effectively, it's 3 topics where you've been able to change your thinking based on your improving maths knowledge, effectively. Have I got that basically right?
Say that again? Sorry.
So basically 3 topic areas where my own increase in maths knowledge will assist me in the way that I teach the subject.
You can do it that way. Yeah, you can choose 3 separate topics if you want, or you can choose an overarching topic for the whole thing.
Okay, I got the impression it was had to be like 3 different bits.
Let me open up the guidance again. don't know why I'm downloading on instead of just opening it. That would have been much easier. But anyway, now I've started. So 3 selected examples from the portfolio, accompanied by a poster analysis. Evidence by examples of impact on people's progress is very important. So 3 different examples of evidence you've uploaded to demonstrate a personal developing subject knowledge from teacher standard 4. Demonstrate breadth. Each example will need to be drawn from a distinct and different area of subject knowledge. Ah, yes. Okay, so actually, what we're talking about needs to be, you need three different things. But for your academic poster, you only need one as the focus of the poster. So, yes. What you want to do is kind of, contrive situations in which you have 3 examples for your portfolio, don't you? So, looking at examples of evidence that demonstrate your personal developing subject knowledge, but they also need to demonstrate pupil progress as well. See, what I was saying was to Hugh earlier was that previously the developing subject knowledge didn't have to be just maths, but here it seems to be suggesting it does have to be. And I guess that's probably better because, for example, I was saying last time someone had chosen to do growth mindset and had tried to improve that with the students in maths classes so that they approach maths better. But it was difficult for him to demonstrate pupil progress, of course, because it's kind of generic. Whereas one person had done negative numbers and someone else done other. But previously, they'd chosen one thing and, well, they'd been given the choice that they could do 1 to 3 different things. But here it seems to be saying, you're right, 3 different examples drawn from a distinct and different area of subject knowledge. So yes, you want to pick 3 things that perhaps you previously, so think about things that you need to develop that was originally something that you perhaps were not so confident in. Plan a lesson, deliver that. So you need to think about 3 areas in which you've been developing your subject knowledge. Look at the theory that goes with those 3 things and draw up a lesson based on that, deliver it and demonstrate how it's impacted. Now, where it says how it's impacted, it could be that it all fell apart, was completely rubbish. That is absolutely fine. It doesn't have to be successfully progressing the students. It's just about how, how successful it was. Then take one of those things, so the thing that you felt was most interesting. See, obviously, you only have to do a certain amount of things. You don't have to do really great depth for the e-portfolio. How much depth do you normally do for your e-portfolio?
There's a reflection on progress.
Right. On your personal progress.
No, I didn't. Well, to be honest with you, my e-portfolio is a mess. I just don't have time to do it properly. Right. So my whole thing about building evidence and that sort of thing up till now has been pretty disastrous. So for this, I'm going to have to start from scratch. I think what I'm going to have to do is look through what we've got coming up on the scheme of work, pick 3 areas, and just go at it like that. And that's literally how I'm going to have to do it. But
I think so. I think
that it crap around the fact I've improved my knowledge really.
Yeah, I think it will be fairly contrived, and definitely start now, to get through things in time.
Yeah, I mean, to be fair, I've actually got a half decent one coming up, because when I go back after half term, my year 10s are starting with ratio proportion, which is something that we looked at right back at the beginning that I wasn't 100% on at the time. Yeah. So, and I've also looked at it as well with my current maths mentor. So that's exactly the sort of thing that I could be doing, and just like contrive it out that way.
Yeah, and it starts off, fairly straightforward. You just need to say what the year group is, what the national curriculum says for that bit, how you built on your prior knowledge, so it was something you struggled with and you had some input and you've done this and that. And then based on what you know about it and some theory, how can you build on what the pupils know to prepare them for learning? So yes, underpinning theory, both pedagogy and subject knowledge. Analysis of how the pedagogical approaches you've used supported pupils in making progress. So obviously that's like, if you were to give them integration, you could say, well, I've given them lots of areas and built it up from their GCSE knowledge, and that was what I thought would be much more helpful than just telling them it and then they didn't engage. Just talking about how we teach things and what's good about it. Diagrams or photographs, challenges, specific activities, so include what you did and why they were effective, and put all of that on a poster. And I think they've been talking about the fact that you could bring along these A1 posters to work at the end and have a whole, wandering around looking at people's posters. I would say that your e-portfolio, generally more, they are going to match it up basically against the teacher standards at the end to decide whether you have passed. So it was
I'm aware of this.
Yeah.
I'm aware that it's a pretty poor state, but I say the first year I pretty much went through solo, trying to teach myself as I went along, because I didn't have anyone within the school that was giving me that regular pedagogical knowledge or anything like that. So I basically taught myself how to teach it. I've now got a maths mentor, so hopefully over this year I'll build up some decent knowledge, but we shall see.
Yeah, and I guess that you can bring that in a polite way, by sort of saying I've had struggled with this and have had to look in textbooks, so you can just demonstrate ways that you have tried to learn and what was effective for you and the differences between that and kids could be or something. But I mean, your ability to write is very good, so you just need to make sure it's backed up by evidence in the portfolio.
It's just really a case of try and think what I want to write, what could I have that prove that, and try and contrive some way of making sure that I've got that in the pedal pad, really.
Yeah, and a lot of things done that way, aren't they?
Yeah. I've done my first couple of assignments doing exactly that, so it's like it shouldn't be too much of a stretch to do it.
Okay. So yeah, when it says this will be presented to peers and all other staff, it's basically for us, for me to mark it and probably print it out. Well, you have to print it out, but probably to show, your peers at the ISW or something. Okay, so yeah, get to it now. I would try and get all those things done by Christmas so that you can then write it up in the bit in between, because I'm guessing that you've got loads of other assignments too.
Yeah, just trying to get this understanding learners and learning one out of the way. That's been a massively contrived one as well, because the due date for it just happened to fall into the assessment period. So actually trying to teach lessons has been a case of where can I squeeze it in amongst tests and marking and feedback on tests. So it's been an absolute, been a bit of a mare, to be fair. So that'll be another one where I try and bend reality to actually fit what I need to put in the write-up.
Yeah. Whereas hopefully with this you can actually go, okay, hang on, let me think of the next 3 lessons I need to plan, if you not needed them for another assignment, then do them for this, or you can use the same one.
Yeah, but I think what we're going to do is, like I say, I think we've got 3 topics to cover between now or when I get back after half term and Christmas break, and possibly 4 actually. And I'm literally just going to focus on those and do it that way. It's probably the easiest way of doing it.
Yeah, absolutely. And I think that in terms of the depth of theory that you need for preparing each of those, really there's just one that needs to be really deep for the poster. The other one should just refer to it a bit in the bit that you upload to the portfolio. But because it's 3,000 words on 3 different things, I mean, that's like 1,000 words each, isn't it? Not even. I mean, I don't know how long your reflections are normally, but I think on a poster you can generally fit about 1,000 words before it starts to look ridiculously busy. I'm just going to actually question that and just have a quick look at. Here is one that I did. I think. This they said. So this was the first one I did, first academic poster I did, and they said it was too busy. But I would be completely happy with you doing that sort of thing. And I think they did show you, there is one on here, an example of one, because you've got to get a lot across. There you go. Well, you guys are the undergrads, anyway. There you go. Oh wow! And they told me I had too much stuff. So, but I think when it comes to it, and look, you can see there's a load of the same ones I've got, like Brilla and Skemp, as you'd expect, and mine were a lot of Brilla, Brown, so I think it works out that you're definitely not going to get more than 1,000 words on a poster. So that leaves you with 2,000 words basically. So kind of like 600 words for each of your reflections. So kind of each of the things that you upload is going to be about 600 words, you know, your reflections. So you're not going to be able to get a huge amount in there. It'll be, here's what the issue was, here's a bit of theory, here's what I didn't know about it from my subject knowledge and what I've tried to do and how I've improved myself, here's what I did to the class, and here's how it was, and let me reflect on that, basically. And then see a bit about that. Okay, so hopefully that's a bit clearer to me now, and is a bit clearer to you. Anything else?
I think we're all good at my end. You just go to, yeah, I might have to drop you a couple of emails over the time just to make sure I'm on the right track. Just
yeah.
The queries and stuff. That's all right.
Yeah, because I don't talk to you till 20th of January, so please email me. I'll put all the answers up on Student Centred self-study tasks. And that's it, really. Do you guys want to talk to each other? Sorry, I see I've overrun.
No, I've got some stuff I need to run on to, so I'll decline that one. Sorry, Hugh.
Me. No, I'm going to pop into work, grab some marking.
Right. Well, I'll let you get on, and good luck with your assignments, and I will speak to you in January.
Right, speak to you then. Enjoy.
Okay.
Have a good Christmas.
Oh yes! Oh
Bye.
my goodness! Have a good Christmas. Bye.